We are live now. Hello and welcome everyone. Thank you for taking your time out and joining us for today's live session. I'm Ritika, event manager at IEEE MAIT, would be the moderator for today's session. All our viewers are welcome to ask their queries in the chat section. Your questions will be addressed in the Q&A session at the end of the workshop. So now I would like to introduce our today's presenter, Mr. Shubh Bansal. He's a quantum computing enthusiast, experienced mentor. He's an ex-intern at Coding Blocks and Ex-Kyrion Technologies. He is skilled in data structures and algorithms, systems design, and web design. He's a passionate he's a passionate sport programmer. He is an expert at Codeforces with a rating of 1632 and earned 4 stars on Codeshift with the rating of 1926. He is currently pursuing Bachelor of Technology degree focused in computer science from Guru Gobind Singh Indraprasth University. Welcome, Shubh. We are grateful to
Hello.
have you with us and sharing your expertise. Thank you for being a part of SkillFest.
Thank you, Ritika.
So, yeah. Without any further delay, let's get started.
Okay, so hi everyone. Hope you are filled with enthusiasm today for the quantum computing webinar. So let's start. I think my screen is visible to everyone, right? So first, like Ritika has already told about me, I am a sport programmer and a quantum computing enthusiast, and you can see about me on various links I provided over here. Now let's get started with quantum computing with a basic history. All right. So just a second, please. Yeah. So in 1928, German mathematician David Hilbert faced problem whether there existed a universal algorithm which can be used on each mathematical theorem to prove it. Yeah. In 1936, English mathematician Alan Turing solved this problem by putting the idea of modern day computers, that is, a single universal programmable computer that could perform any algorithm. Then in the year 1985, English physicist David Deutsch posed that computer and man both are physical systems and both perform algorithms. So is there a single universal computing device that can simulate any other physical system? So therefore, there will be no need to rely on informal or heuristic arguments to justify the notion of algorithm. Arguments, you could use the laws of physics to prove the algorithms on that device. And he observed that modern day computers took too much time to simulate quantum mechanical systems. And hence he created his own quantum computer in the year 1985. Now, what is a quantum computer actually? So when people hear about quantum computers, they start thinking about mobile phones or like normal classical computers like desktops, laptops, and they think that quantum computer would be something like that. But no, quantum computer is fundamentally different from classical computers. It uses properties of quantum physics like quantum entanglement and superposition to store the data, and it performs the computations on that. Now, the basic unit of a classical computer is a bit. Like, yeah, it can store a zero or a one. In a similar fashion, quantum computer has a basic unit of memory, which we call as a quantum bit or qubit. It is the natural computing model than conventional computers. Now, let's talk about power of a quantum computer, right? Why are we studying quantum computers? So, it has the potential to solve world's most complex problems. Like we say that if we have a classical computer and it has n bits, all right, so it can represent only a one state at a time. On the other hand, a quantum computer having same number of bits can represent 2 to the power n states at the same time. It has a potential to disrupt online security, cryptography applications, and much more, like in machine learning, AI. And there are many exciting algorithms like Shor's algorithms to factor large numbers and Grover's algorithm to learn to search an unordered list in square root time. Now, now we will talking about some facts and some things about quantum computers, about its basics, and how we can use those facts, how we can use those things to build up a basic quantum program. Right. So first we need to revise out our matrix multiplication. I hope everybody is familiar with matrices and matrix multiplication, but still I'm going to go through in some seconds. So if we have two matrices, so how we have to multiply them, we have to take their product. So it will be multiplying all the rows with the corresponding column of the another matrix. And we generate a product matrix with dimensions n cross m, where n being the rows of the first matrix and m being the number of columns of the second matrix, right? Next, we have tensor product. I think most of us would be unfamiliar here with what is a tensor product. So tensor product is again of an operation for matrices. So we take two matrices and we multiply the right matrix with each and every unit of the left matrix. So here, if we can, uh, here as you can see, we have multiplied x0 with y0 and y1 matrix and x1 with y1, and we have got our complete tensor product, right? Similarly, if we have to take tensor product of multiple matrices, it is done in the similar fashion, where we take the left matrix and multiply each and every entry of it with the complete right matrix, right? Now, next we'll move on to the two quantum mechanics concepts which are used in storing the data in quantum computers. The first one is quantum superposition. Just like a classical bit, it can be both a zero or a one, right? It can be a zero or a one. A qubit can again be a zero or a one, or it can be both at the same time. It does not mean that secretly it is a zero or it is secretly a one, but it clearly means that it is both zero and one at the same time. Next is quantum entanglement, right? So if I talk with respect of quantum mechanics, quantum entanglement states that if we have two physical systems, so their properties, their states are defined with respect to each other. We can use the properties of one of the physical systems and define and determine the properties of the other system. In respect to quantum computing, two qubits are in superposition when they are correlated with one another. So let's see what is qubit. So qubits are, just as I said, qubits or quantum bits are the basic building blocks of quantum computers. Just like a classical computer has classical bits, 0 or 1, a quantum computer has 0 or 1 or another qubits, right? We'll see what this another means right now. So it has a state just like a classical bit, right? And the state is represented as a vector in 2D vector space. And these qubits, these can be stored in photons, electrons, neutrons, so like subatomic particles. Now, during this presentation, I will first connect the idea of a quantum computer with respect to a classical computer, and will then see it through the sole perspective of a quantum computer. So if we connect the idea of a classical bit to a qubit, so we have 0 here as a 0 qubit and 1 as a 1 qubit. Here these symbols you can see, these are the bracket or the Dirac notation. It's nothing fancy. It just says that the 0 or 1 is resting as a vector, right? If you see the expansion, so here the 0 is like 1 and 0, and this one is a matrix with 0 and 1. So the 0 and 1, these are computational basis states. Now, what does a computational basis state mean? Like I said, again, then in a quantum computer, 0 and 1, they are similar to classical bits. And instead of 0 and 1, we can have both 0 and 1 at the same time. So the rest of the positions, which means that the 0 and 1 are at the same point of time, these are the superposition states. whereas the 0 and the 1, these are computational basis states, and they have all the properties of the classical 1 bit and 0 bit. Now, the general state of a qubit, all right? So, as I said, that a quantum bit can be equal to both 0 and 1. This is how it is done. So, we have a 0 bit and a 1 bit, and both of them have amplitudes alpha and beta. The amplitude of 0 here, as you can see, is alpha, and amplitude of 1 is beta. And alpha and beta can be complex numbers also. But you cannot just randomly assign anything to alpha or beta. There is a little constraint. We will see that afterwards. And if you see, I just said that there are these brackets. These are the these are the ket notations, bracket notations, or the Dirac notations. And if we want to express a general qubit in the form of matrix, this is how it is. So if you can see that this alpha is basically the magnitude of bit 0, the amplitude of bit 0, and beta is amplitude of qubit 1. So if we come back to this slide and we see 0, 1 qubits in the matrix form, we can see that 0 qubit means that the magnitude is completely 1 for 0, and amplitude is 0 for 1. And in the 1 qubit, amplitude for 0 is 0 and amplitude for 1 is 1. That's why you can say that this qubit is in a computational basis state. And like I said, that in the qubits, these can also be complex numbers, or these can be other than 0 or 1. This is how it is done. So alpha and beta here have values 1 plus iota by 2 and iota by 2. These are the positions of the qubit in the 2D complex vector space, right? So as I said, you cannot just assign alpha or beta something. There is a constraint, and that constraint is called the normalization constraint. According to this normalization constraint, alpha square and beta square, the sum of them should be equal to 1. That is why the length of the state is always 1. And we call the quantum states are unit normalized vectors. As I took an example here, you can see 0.6 and 0.8. These have, the qubit 0 and 1 are having amplitude 0.6 and 0.8. If you take sum of their squares, it comes out to be 1. That means that this is a valid qubit, right? And if you take sum of these, so if you take a sum of these alpha and beta, it will come out to be the normal qubit. Now, we have talked about single qubits. What about if we want to represent multiple qubits? So for representing multiple qubits, we take their tensor product. So if we have a qubit 0, 0, so what does it basically mean? That it is tensor product of qubit 0 and qubit 0. And according to the tensor product, the matrix will come out to be this. So here we have multiple examples of what a tensor product of two and multiple qubits look like. For 0, 1, it comes out to be 0, 1, 0, 0. And for 1, 0, 0, which is binary 4, it comes out to be 0, 0, 0, 1, 0, 0, 0. So the tensor product is actually the product state of a qubit. And product state, these can be factored back into the individual qubits. So we'll see how this is relatable in the next part. And I would like you to notice one thing over here, that for every 2 qubits, the size of the matrix is 4. For qubits, there are 3 number of qubits, the size of the final matrix is 8, which is 2 to the power 3. And here it is 2 to the power 2, 4. So as I said in the beginning, that if a quantum computer has n qubits, it can represent 2 to the power n quantum states at one time. Now let's move on to quantum logic gates. So when we are studying programming, all right, so what did we learn first? That we have a machine and we have to interact with that machine. So the first thing that we gathered was data. Yeah. So if you remember your primary classes, sorry, if you remember your first classes of programming, you would have learned about data types like int, float, number, string, right? So now we have learned about the basic data of quantum computers, which is a qubit. And now we are going to apply operations on these qubits. So what are the four basic operations that we can perform on a bit? So if you remember back your classes, or if you just take a simple bit, for example, a zero, what all things can you do with that zero? There are basically four basic operations, and these are very intuitive. So the four basic operations are identity, negation, constant zero, and constant one. All right. So if you see them as functions, so these come out to be f of x is equals to x, which is identity function, and the negation of x is f of x, the constant zero and constant one, which takes any bit zero or one and transfer it to, if it is constant zero, it transfers it to the state zero, and if it is a constant one, it transfers it to the state one. If you look at this from an other angle, so we have 0 and 1, and applying identity gives us 0, 1. These are the diagrammatic representations. And as I said, that 1 and 0 can be represented in the form of matrices. So here we are. If we take this, the 1, 0, this is a 0 qubit, right? So if we multiply with this matrix 1001, which is basically our identity matrix, we get 10 again, right? The negation matrix, as you can see, this is 0110. And if we multiply these two matrices, that is, if we apply the negation on 10 qubit, we get 01. And 01 is actually bit qubit 1. And here goes for constant 0 and constant 1. So constant 0 turns any qubit into 0, and constant 1 turns any qubit into 1. Now, we must note one thing, that quantum computer works only on reversible operations. When I say reversible operations, it means operations where if we are given an input and output and a gate, then the the operation applied on input is giving some output, and again same operation applied on that output will give us back the first input. So that is what a reversible operation means, right? So operations which permute are reversible, which just tangle with the your inputs and does not overwrite or change them. Those operations are reversible. But operations which rewrite your data, those are irreversible operations. And interesting fact that all quantum operators that we will are going to discuss, they are their own inverses. Now, quantum gates, yeah. So quantum gates are nothing but just matrices. So as we have seen here, we have applied our first gate, which is the X gate, the quantum X gate. Yeah. So these are nothing but matrices. So first we'll talk about our X gate, which is in respect to classical computers. As I told you that first I'll tell you with respect to classical computers, and then we will look at it from a quantum computer perspective view. So in respect to classical computers, the X gate is simply your NOT gate. If we apply a NOT on a 0, it turns it to 1, and a NOT on 1 turns back to 0. If we apply this X gate on our any of the qubits, so a qubit's general state was this: alpha 0 plus beta 1 gives us beta 0 and alpha 1. You can clearly see here that the magnitudes have been switched. Yeah, alpha was the magnitude of 0, and after applying the X gate, it has become magnitude of 1, and beta was magnitude of 1, which after applying X gate has changed to switch to bit qubit 0. Yeah, this is how we apply on unitary qubits. So this is now from the quantum computer perspective view. This is our X gate. Yeah, this is the symbol for X gate. And this is the matrix. As I said, that all the matrix, all the quantum logic gates and all the processes are merely matrices. So since X gate is a quantum computer logic gate, it has to be a matrix, and this is a X matrix. Yeah. So in X was inverse, and we can see that applying it on a qubit, this is qubit 0. Magnitude of 0 is 1 and magnitude of 1 is 0. So this is a qubit 0. And applying a X operation on this qubit will give us qubit 1. 0, 1 is qubit 1 and 1, 0 is qubit 0. And applying the same operation again. Now consider this was our first input, and this we got this as our output 0, 1. Now if we apply X matrix back to 0 and 1, what we will get? So we will get back our first input 1, 0, which is our qubit 0. So you can see here, applying it on an input gives us a certain output. And if we apply back a quantum process on that same output, we will get back the original input. Now let's try it out with a different qubit. All right. So with a different qubit, I mean with a superpositioned qubit, where a qubit is both 0 and 1. So a qubit which is both 0 and 1 will look nothing fancy. It is just again a simple matrix. And here it is. Sorry, this is interfering a bit. So this is the matrix for a this is a matrix for a quantum superposed qubit, which is has magnitude alpha, which is 1 by 2 for amplitude of 0, and root 3 by 2 is amplitude of 1 beta. And if we apply the X gate on it, so we have the inverse of our original qubit, which is root 3 by 2 and 1 by 2. Now, what is basically this root 3 by 2 and 1 by 2? So if we talk in the sense of quantum computers, this 1 by 2 and root 3 by 2 are basically the probabilities of this qubit turning to a 0 or a 1 at the end of the computation. All right. Then now for a superposed qubit, a measurement is required later. All right. So before the measurement, it is either a 0 or a 1, and alpha and beta are basically the probabilities. Now, the second gate, which are we going to discuss, is the conditional NOT gate. So C NOT gate. So the C NOT gate is just like the if else of the classical computer, and it takes two qubits, out of which one is the control bit and the second one is the target bit. So if the control bit is 1, it leaves the target bit, it flips the target bit. But if the control bit is set to 0, it leaves the target bit unchanged. And also the control bit is always unchanged. We will never tamper in the C NOT gate a control bit. If we see this diagram, you can see that the first bit is the control bit and the second bit is the target bit. So in both these operations, the control bit is 0 and target bit are 0 and 1. Since the control bit is 0, it has leave these target bits untampered and they are same 0 and 1. But if we talk about these two operations where control bit is 1, so and the target bits are 0 and 1, so these have been reversed to their alternate magnitudes. Yeah. So if we applied C naught, this is how we represent a two qubit system in vector notation, in a direct notation. So if we apply C naught gate on a 0, 0 qubit, we will get 0, 0. And on 0, 1, we will get 0, 1. Again, as I said, since the control bit is 0, the target bit will be unchanged. And on the below 1, 0 and 1, 1 qubits, applying C naught gives us 1, 1 qubit for 1, 0 and 1, 0 for 1, 1 qubit. Now, this was the classical computer point of view. From the quantum computer point of view, C naught gate is again a matrix. This is the symbol for C naught gate, and this is the matrix. As you can see, is in this matrix. So these are the entries 1, 1, and it is kind of a mixture of identity matrix and the X matrix. All right. So we will see how this is working in further examples. So first of all, if we apply this C not gate on our the C naught gate on our 00 qubit, we will first have to take their tensor product 10 and 10. The tensor product comes out to be 1000, and the C naught gate is actually a matrix which was this. So we take the product of these two matrices, and what we will get is 100. And in the start I said that a tensor product can be factored back into its individual qubits. So here we factor back this tensor product, our product state, into the individual qubits, and what we get is 00 qubit. Since the control bit was set to 0, the target bit was left unchanged. This is what is actually happening inside a quantum computer. This is how the operations are going on. The matrix multiplications are going on basically. So if you see again with 0, 1, we have to take the 10 and 01 tensor product, multiply it with our C naught matrix, then we obtain a product state which we have to factor back into individual qubits, and qubits come here to be 0 and 1, just like it was in the start. Now, if we apply the C naught gate on qubits where the control bit is set to 1, we see that the product state comes out to be different this time from what we had initially. This is because the control bit is 1, and now the target bit will be tampered. So after applying the C naught gate and factoring back the product state, what we get is 1, 1. So you can see that the input was 10 qubit, but we got 1, 1. Since the control bit was 1, the target bit was flipped. And same for the 1, 1 qubit. Since this is control bit is 1, our 1 target bit will result into the 0 target bit. And this is again all the process which is going on, all the matrix multiplication. Now the third gate is our Hadamard gate. So Hadamard gate is a pretty interesting gate. It takes a 0 qubit or a 1 qubit and it puts it into exactly equal superposition. Exactly equal superposition means, again, I'm saying that exactly equal superposition is when a qubit is either when a qubit is both 0 or 1. Both meaning both 0 or 1 means that it can collapse to either 0 or either 1 at the end of the computation when we will be measuring our qubit. And because of the Hadamard gate, we can transition in and out of our superposition. So if you see that we have applied our Hadamard gate on the 0 qubit and 1 qubit, and it has brought the qubit into superposition by changing the amplitudes alpha and beta to 1 by root 2 and 1 by root 2. If you take the sum of the squares of these two amplitudes, you will surely get 1. Same for the 1 qubit, which has amplitudes now 1 by root 2 and minus 1 by root 2. Again, you may notice that the sum of the squares will be 1 itself, and it is perfectly satisfying our normalization constraint. Now, from the quantum computer point of view, again, the H gate is a matrix since it is a quantum process gate. And if we apply this H matrix on our 1 qubit, 0 qubit, and on 1 qubit, this is the output which we get. Yeah. So these are alpha and beta, the amplitudes of 0 and 1. And it has put our 0 bit and our 1 bit into exact superposition. So, but wait, didn't we discuss that these quantum processes, these all logic gates, are reversible computations, right? So that means if we can take a qubit, 0 or 1, and put it into exactly superposition, this might mean that if we have a qubit in superposition, we can shift it back to 0 or 1. Yeah. So yeah, we have a Hadamard gate, 1 by root 2 and 1 by root 2. This is the matrix. And if we apply it on a superpositioned matrix, what we get back is our 1, 0 and 0, 1, and which were basically the initial qubits, the computational basis states, the 0 and 1 qubits. So we can transition out of superposition as well. So now let's have some play time. All right. So we have talked about these facts and these things, the quantum logic gates, qubits. and how the processes are going on. So now we will build a small quantum computing program by using the Qiskit framework from IBM. So just give me a minute. Okay, so first we will be going on to our IBM Cube Experience website and see what a quantum computing circuit looks like. We will study its elements and build one. All right. So, okay, yeah. So we have our, this is the dashboard of IBM Cube Experience, and we will now compose our circuit. So first of all, let me tell you about elements of this quantum experience. Yeah, so this is basically our quantum circuit. These Q0, Q1, Q3, Q2, these are our qubits, the actual qubits, which will store our data. And this C3, these are basically, this whole line is basically for our classical bits. The actual value of a qubit, which will be measured, will be stored in these classical bits. Now, these wires, since this is a circuit, you might be thinking that these wires are electric wires, but no, these wires represent time. These are time wires. All right. So this is t equal to 0, t equal to 1, and so on. So now we will be creating a small circuit to represent quantum entanglement. All right. So as you can see, these are our gates. Everything, every process or every quantum circuit basically is a matrix in a quantum computers. So first we will put our we will take only 2 bits. All right. So first we will put our first qubit Q0 in a superposition by using the Hadamard gate. Initially these Q0 and Q1, all the qubits are 0. If you want to change any qubit to 1, you can use the X gate. Right. And now we will be using this Hadamard gate to bring this Q0 to superposition. All right. Now, after we have brought this into superposition, that means it will be, it will have equal probability of being a 0 or being a 1. All right. So now let's add a controlled NOT, the C NOT gate. So what this C NOT symbol represents, the C NOT symbol represents is that this is the control bit and this is the target bit. So if the control bit is 0, the target bit will give us a 1. Sorry, the target bit will be remain unchanged. But if the control bit is 1, it will flip whatever the value is target bit. All right. So we have applied a Hadamard gate to bring our control bit into equal superposition, and then we have applied a C naught gate. Now let's measure both of these quantities. So this is the gate, this is the operation which we will use to measure the our qubits. All right. So these are basically your, what we can say is expected outcome. All right. These are your expected outcomes, and this is your Balog sphere. So nothing to learn about this as of now. Now we will going to run our quantum circuit, this quantum circuit on an actual quantum computer, which is resting there back in America. All right. So we can select our run settings. The backend means whichever quantum computer you want to run on. So we have quantum computers with 5 qubits, with 32 qubits, even with one qubit. So let's select the 32 qubit IBM Q quantum simulator and shorts. So what are shorts? Shorts are basically the number of runs you perform on your compiled program, all right, compiled circuit. So we have 1024 shorts over here. Now let's run this circuit and see what we will get as our output. So the job has been sent to the quantum computer and the job is complete. And we have actually run a quantum circuit on an actual quantum computer. So yeah, so this is the window. We have our output over here. So you can see that all the details about the quantum computer, the timestamp, and the quantum computer which we ran our code on, right? The number of shots we took, and here is our actual output. So you can see that for a qubit 00 and for qubit 11, these are our outputs. What does this output represent? So basically, this output represents that 50% of, sorry, 48% of the time we got the bit 00, and for 51% of the time we got the bit 11. What does this mean? That for a 51% of time, the superposition Q0 bit fell to qubit 1 after measurement, and the second bit, which was our Q1 bit, since it was the control bit was 1, the Q1 bit flipped to 1 state. This happened 51% time after from these 1024 shots, and we got the 00 bit, that is the Q0 bit fell towards 0 for 48% of time. You may note that this is not exactly 50-50% because the quantum computer is because of some errors in the like quantum computers, right? So here we can see our original circuit, the transpiled circuit, and here is the code which was generated for a Qubit script. All right. So now we will try to write this circuit. We had this circuit, and now we will try to write this circuit from ourselves in a Qubit program. Right. So we have our Python notebook over here, and Qubit is IBM's quantum computing framework. It is written in Python, and you can learn that. You can program quantum computing circuits, and it is like really fun. Okay, so first of all, we are going to import the Qubit framework. Okay, so we have imported our Qubit framework, and if you remember the circuit, first we have our qubits and the classical bits. So we are going to create qubits first. So let's name it as QR, the quantum bit register. So we need 2 qubits. So
Excuse me,
we have
sir.
to, yes.
Can you increase the font size of the program?
Okay.
Thank you.
Okay. So I think it's pretty clear now. So first we have created our 2 qubits. If we look back at our circuit, just a second, please. And, yeah, okay, we here have. Okay, so here we have our quantum circuit which we created. All right. So in the quantum circuit, we have our original circuit. So first we have the qubits and the classical bit storages. So we have created our quantum bits. The two qubit system has been created. Now we will be creating two classical bits to store these, to measure these qubits. So let's name it CR. All right. So we have created two classical bits. Now let's try to see what does the quantum circuit till now look like. Right. Yeah. So let's see what the circuit looks like. Yeah. So first we have to create this circuit, and we have to pass on the bits which are QR and CR quantum bit registers. All right. The circuit is created. Now we will be using matplotlib to view our circuit. So we have imported our matplotlib. So we have to draw this circuit. Matplotlib. Sorry, first without this. So you can see that this is our circuit, which it looks like. So qubit 0, qubit 1, and two classical bits. All right, pretty much like this only, the circuit. Now let's make it a bit fancy. So we'll have, um, yeah. So now it looks pretty better than what it was looking like. So it have a graphical representation now instead of the text based. All right, so we have created two quantum bits and two classical bits. Now, in this circuit, which we had originally, we had a Hadamard gate. So first, we are going to add a Hadamard gate on our first qubit. So we will do that by writing this command, Hadamard, apply a Hadamard gate on qubit 0. So you can see that the result has been created. It is that instruction has been set. And now let's see what our quantum circuit looks like. So it looks like this. There is a Hadamard gate on our first qubit. All right. Now, after this Hadamard gate, okay, so I think it's visible right now. So the after this Hadamard gate on our circuit, remember we had this C naught gate. All right. So we have to add this C naught gate, or you can say this as a CX gate. So circuit dot CX. We have to put this gate where the control bit will be the QR0 bit, and the target bit will be QR1 bit. The instruction has been set. Let's see how the program looks, the circuit looks like. And so we see that we have a C0 gate on our quantum circuit. So this was only the circuit, and now we have to measure these qubits. So to measure these, we are writing the command. We have to measure these. We have to measure QR in CR. Instruction has been set. Again, let's look. So this is the circuit. The 0th quantum bit will now fall into the 0th C0 bit, and the qubit Q01 will fall in classical bit C1. All right. So this, we have created our quantum circuit, and now we are going to run this quantum circuit, but it will be running only on a simulator, which is there on this system. All right. So to run this simulator, we have to write commands, and we are going to write. Okay, so first we have to, again, this circuit is clear. Now, before running it, we have to actually measure it. So to measure, we take it and write measure. All right. So how do we measure it? So to measure, sorry, yeah. So to measure, we have to, yeah, I think we have measured already. Sorry. So we have already measured this qubit, and now we are going to run it on a simulator, and let's store this result in a simulator equal to, and we have to use the backend, and the backend will be the Quantum simulator. All right. On the IBM Q experience, we ran our computer on that Quantum simulator, on the quantum computer, which was having 32 qubits. All right. So we are going to run this on our 32 qubit quantum simulator. Get the, so we have an error over here. Just a second. Oh, sorry, we have a wrong command here. Okay, so we have these commands of it. First, we have to write only quantum simulator, and now we have to get its result as, sorry, we have to get the result by executing circuit, and the backend is the simulator which we created, and the result method on this. And now we have got our result. All right, and now to view this, we have to import the matplotlib to, sorry, we have to import it from the Qubits visualization tools import plot histogram. Okay. Oh yeah, sorry, sure. Dot tools dot visualization. Yeah. So we have our plot histogram right now, and we are going to plot our shorts counts. So plot histogram and result dot get counts on circuit. So you can see there, you can see here that we have our histogram, and just like we obtained it in our IBM Q experience, we had 00 qubits and we had 11 qubits. The chance for 00 was of 47%, and for the 11 qubit, it was 52%. All right, so we have got a similar result on our simulator. And if you look at this code, if we look at this code from start, it will be, okay, I have to, second. Okay, so if we look at this circuit, the Qubits program which was generated, all right, this was the program auto-generated by the IBM Q experience. And if we look at the program which we have written, it is one and the, like, it is too much similar. Okay, so it has created two quantum registers, two classical registers, And here again, two quantum registers, classical registers, and display to the circuit. Then apply the Hadamard gate on the circuit by on the 0th qubit, then a CX gate from 0th to 1th qubit, and then it has took a measure of both of them. Yeah, all right. Okay, this was the quantum simulation which we ran with the help of Qubits kit. All right. So now you can also view. You can have more resources. You can check out these resources to learn more about quantum computing. The IBM QS Kit channel on the YouTube, Microsoft Quantum Katas. So Microsoft Quantum Katas, Microsoft is trying to, again, all of these companies, Microsoft, IBM, Google, even Google, they are trying to recruit more and more people in the field of quantum computing research because, quantum computers are like, they are the next big thing. All right, they are the next generation of computers and they are going to revolutionize the whole field of computers. So the next fields which are coming upon are QML, QAI, and more like that. The cryptography which we have right now, it will become obsolete because of quantum computers. So much research is going on in the field of quantum computing. You can learn about these on Microsoft Quantum Katas, on IBM QScript videos, and there's a really good blog written on quantum.country/QCVC. All right. So if I show you the resources, quantum.country/QCVC. So quantum computing for the very curious. It is a really good blog. It explains about the history and it uses very good language and explains about quantum computing from the very basics. You can check this out. If I talk about Microsoft Quantum Katas, okay, so here is the page for Microsoft Quantum Katas. They are starting explanation by from the very basics, the complex arithmetic, linear algebra, then they move upon to qubits, multi-qubit systems, okay, and the next application. Microsoft has developed their own language for quantum computing, which is Q Sharp. You can try out that. I program on Qubits Kit as of now, and so next we have these. Yeah, that's all for now. You can build your quantum circuits on IBM Q Experience just like I did. You can try out these programs in Qiskit. You can learn Qiskit from YouTube, from IBM's blogs, and Qiskit and Microsoft QHash. Both of them are open source projects, so you can try and contribute to these Qiskit and QSharp. And if anybody here wants to, they are looking for any GSOC opportunities, if they find quantum computing interesting. So the GSOC is also focused towards some organizations which are doing research work in quantum computing. For example, Qtip came up with a pretty interesting project and came in GSOC last year, right? So that's it for today. Thank you very much.
All right. We had a really amazing session. I hope our viewers have received a great introduction to quantum computing. I really appreciate the response of our attendees. We have received quite a lot of questions. So let's begin with our Q&A session. So we have our first question. Uh, there on the screen. Which software is best for quantum computing?
Okay, so software, as in, I think you are talking about language, maybe. So the best you can say for, okay, so I think, yeah, so you're saying about ID or something. Okay, so for quantum computing, again, you can program in Q sharp language from Microsoft, or using Qiskit from IBM, and both of them are programmed with the help of Python. You can look at the documentation on the respective websites. So these two are best as of now.
All right. Okay. So we have a next question. It asks, what does RZZ mean?
Okay, so RZZ, again, is a RZZ is a gate for quantum computing. As I said, so RZZ gate is an, again, a matrix, and it applies on 2 qubits, I guess, and it performs operation on that. Okay.
Okay. So our third question is from the same guy. He asks, sir, what is Q sphere?
Okay, so Q sphere is the block sphere. It represents the quantum state of a qubit. All right. If we see on the screen, if we see our simulator, yeah. So here is the Q sphere. This Q sphere tells us about the state of the qubits which we will get. You can see that there are 3 qubits over here right now, and none of all of them are set to zero. Initially, all of these are zero, so the result would always be 0, 0, 0. Okay, but if I apply some operations, like if I had a Hadamard gate over here, so you can see that it can fall into either 0, 0, 0 or 0, 0, 1. Again, if I'm trying to apply some other gates, so this is the block sphere. It will tell us about the quantum states of the final quantum circuit which we have.
All right. So our next question is from Vaibhav Gupta. He asked, do we have a career opportunity in quantum computing when we graduate in 2022 or 2023?
Yes, yes, there are, in fact, there are pretty interesting opportunities in quantum computing. As I said, IBM, Microsoft, Google, they are all are investing a lot of money in quantum computing. You can check out their websites, and they are hiring research interns for quantum computing. I think the IBM hirings are open right now, and if you have a grasp about what is quantum computing, you have done a bit of much work, so they'll hire you, and you can start interning with them, and the career is pretty great in quantum computing.
Okay. So our next question is from Sanchit Vishwakarma. He asked, we haven't made a quantum computer yet, have we?
No, quantum computers are there. The IBM has a quantum computer. Google has its quantum computer. In fact, the circuit which I run right now on that IBM Q experience, it was actually ran on on a real quantum computer. So they exist. Yeah. In fact, I would like to share an interesting fact. So during the initial phase, the quantum computers were basically worked upon to achieve quantum supremacy. Right. So what does quantum supremacy means is quantum that just like we built a circuit. All right. So there would be a time when this circuit keeps becoming more and more complex, and when we run it on a quantum computer, the quantum computer will perform that operation in a certain amount of time. But if we simulate the same process on a classical computer, the quantum computer will outrun it. And Google says that it has achieved quantum supremacy. The news is of around October end last year, and they said that they have achieved quantum supremacy. They ran a program on quantum computer which took only 3 or 6 minutes, but they have expected that the same program will run on a classical computer for more than 10,000 years. So yeah, we have made quantum computers. We have even achieved, I think, so quantum supremacy, as Google said.
All right. So our next question is, um, sir, which type of coding we will learn in quantum computers?
Okay, so as I said initially, that when people hear about quantum computers and the term computer in it, they relate to classical computers. But like it's not relatable to what we are studying right now, likely. So as I ran a program for quantum entanglement, the circuit which I made was for quantum entanglement. Okay, we were playing with the qubits right now. When you have initially learned the programming language, you would have probably learned about how to print "Hello World." Okay, in maybe C++ or Python, you would have printed "Hello World." But today, if you have run your first quantum computer, the quantum circuit, and it was a quantum entanglement. So quantum computing is going to be a bit different than the conventional programming we are actually doing right now.
Okay, all right. So our next question is from Amrita. She asks, why are the quantum operations reversible?
Okay, it is like why are they reversible is not I think this is so quantum computer basically works only on reversible operations. It is not like it can work on irreversible operations. It only works on reversible operations. So all the gates which I showed you right now, the Hadamard gate, the X gate, the CX gate, they all were reversible operations, and it runs on reversible operations because the qubits which are involved, the basic information in quantum computers, we are using the fact that they are in superposition. So for using that advantage, for using quantum entanglement and superposition for our benefit, the operations are limited to only the reversible operations.
Okay, all right. So our
But
next question.
we can simulate those irreversible operations on the reverse in the form of reversible operations. You can read about Deutsch-Oracle theorem if you want to learn more about this.
Mm, all right. So our next question is, if I have to choose between competitive programming and quantum computing, which one should I go with? Like, I guess the
So
person asking this question is doing his graduation.
yeah, okay. So I always prefer that you first do basic building of your problem solving skills. So before quantum computing, there was again web development, AI, ML. All right, people used to go in. People always had this question in mind whether we should start with competitive programming or we should go with web development or AI or ML. Now quantum computing has been added to this list. So the first thing that engineering student should always do is first clear out the basics. So I think competitive programming is a very good way for that. If he does the basics of competitive programming, that is basics of data structures and algorithms, trees, graphs, and he has a really good problem solving skills, then he could be a better quantum programmer. All right, could be a better quantum computing scientist than he would be if he starts quantum computing directly. So I should say that go with competitive programming first, obviously, and then quantum computing.
All right. Uh, okay, so we have our next question. It asks how to apply C naught, which is CNOT, on superimposed qubit.
Okay, yeah, this is a nice question. So if we take an example, okay, let me share my screen.
Guys, I'm really sorry about this thing that we are not able to flash your questions on the screen. We are currently facing some network issues, so please pardon us for that.
Okay, so I think everyone is able to see my screen,
Yes, it is
right?
visible.
Yeah, okay. So if we take a quantum superposed bit. Okay, so it would be, let's say, 0. Please excuse me, 0 plus 1 by root 2 with 0 and 1 by root 2 with 1 qubit. All right, as I said in my slide, that both of these are, this is a qubit, and they are perfectly they're in perfect superposition. If you take sum of 1 by root 2 and 1 by root 2 squares, it will come out to be 1. So this is in a state of superposition. When I showed you the C naught gate, it was in either 0 or in 1. But if we apply the C naught gate on this quantum bit, okay, this is the control bit, let's say. This is the control bit, and for the target bit, take a 0. All right. So if we apply the C naught gate on this complete thing, if we apply the C naught gate on this complete thing, so what we would have is, we would have C naught. So okay, first we will writing it like this. I'll take it Cx, not on x is the same. The C naught is also called Cx. Cx on, so we will multiply this 0 qubit with this 0 and 1. So it will become 0, 0, yeah, and 1, 0. So as I explained that controlled X, controlled NOT gate works on 2 qubits. So we have obtained the 2 qubits from this expression, and upon that we can take root 2. Now we can individually apply the controlled X on both of these qubits. All right. So if we take it like this, plus controlled X on. So this is how a controlled NOT gate will be applied on a superposition or a qubit which is not a 0 or a 1. So we can apply this controlled X on 0, 0 and controlled X on 1, 0. Again, the basic 0 and 1. Okay.
All right. So, sir, we have also received various questions regarding the resources which they can refer to for learning quantum computing, and what are the basic languages which one should know to get started with quantum computing.
So the language which you need to know is Python, because Qiskit and Qsharp both are written in Python. So you have to know Python first to start with quantum computing. And what was the question again?
And the
Languages
resources,
and yeah. So
languages, yeah, languages and the
resources.
yes.
Okay. So the language was, again, as I said, Python. You have to know Python before you get started with quantum computing. And for the resources, as I shared, the quantum katas by Microsoft, IBM, Experience, and Qiskit from IBM, you can use that to start. You can refer their website, and you can see QU tips blogs. You can see the quantumcountry.qcvc's blog. Right? These are pretty great resources which you can refer to start learning about quantum computing.
All right, sir. I hope we have answered or addressed majority of the questions asked by our attendees. And if we somehow missed any of the questions, then you are most welcome to ask them in the WhatsApp group. So, and lastly, I would like to ask Shubh, is there anything which you would like to cover before a wrap up?
Okay, yeah, so I would like to say that you should get started with quantum computing, because quantum computing is going to revolutionize the whole field of computers. So, like your classical computers, we had ML, AI, cloud, AR, VR. So these all technologies are again going to be recreated in the field of quantum computing. And if you get started with quantum computing, it would be a great benefit for the career, and it would be a great benefit for our whole world. We could be progressing in the development of science and technology much more. Yeah, that's all.
All right, so great. Thank you, everyone. We are grateful for being with us throughout the session. And thank you so much, Shubh, for joining us for successfully presenting this workshop. And yeah, stay tuned with our social media handles, links to which is given below in the description. And yeah, subscribe to our channel, press the bell icon, and to get the updates for our upcoming sessions. And yeah, lastly, stay safe and keep learning.